Welcome to Data Structures in C. In this first lesson, we learn why data structures matter so much. We will see how the way we organize our data decides if a program is fast or slow. Along the way, we meet a few big ideas: the logical view versus the physical view, abstract data types, the cost model, and how memory works in C. Let's start with a simple question. Why do data structures matter at all? The next few slides show how much of a program's speed depends on one thing: how we store our data. Imagine 1 billion records. A user asks one question. The simple idea is to check the records one by one, from the top of the pile to the bottom. Let's count that work. If the data is one big unorganized pile, we must look at every record. 1 billion records means about 1 billion comparisons. At one comparison each microsecond, that is about 17 minutes for a single question. We call this cost big O of n. Now let's organize the same data. With a balanced tree, we need only about 30 steps. With a hash table, about 1 step. Same data, same machine, but now the answer comes back in microseconds. We call this big O of log n, or big O of 1. So what changed here? Not the data, not the machine, not the question. Only the structure changed. That single idea is the heart of this whole course. Let's count the work by hand. We have 5 record keys dumped in no order. We want to find 7. Nothing is sorted, so we must compare from the left, one key at a time. Index 0 holds 17. Is that 7? No, so we keep scanning. Index 1 holds 4. Not 7, keep going. Index 2 holds 91. Still not 7. Index 3 holds 52. Not 7 either. Index 4 holds 8. Close, but not 7. And now the pile is empty. 7 was never here, so the answer is not found. Count the work. 5 keys meant 5 comparisons. When the value is missing, we touch every item. That is the worst case. When the value is present, on average, we touch about half. Either way, the cost is just the number of items we check. Let's play a quick game. I pick a number from 1 to 100. You guess a number, and I tell you higher or lower. Before we start, make a real guess of your own. What is the best first number to try? And how many guesses do you need to find any number? Is it 70, 25, or 7? Pause and decide. Here is my secret number, 73, and here is how the game runs. Guess 1 is 50, right in the middle. I say higher. So we throw away 1 to 50 and keep 51 to 100. Guess 2 is 75, the middle of what is left. I say lower. So we keep 51 to 74. Guess 3 is 62. I say higher. We keep 63 to 74. Guess 4 is 68. I say higher. We keep 69 to 74. Guess 5 is 71. I say higher. We keep 72 to 74. Guess 6 is 73. Correct. We found it in just 6 guesses. So the best first guess is 50. Whatever I answer, you drop half the numbers. Halve and halve again, and you find any number in at most 7 guesses. Not 70, just 7. The same trick scales up. 1 billion records take about 30 halvings. The whole population of Earth takes about 33, and each time the data doubles, you pay just one more guess. When a program is slow, our first idea is often to buy a faster computer or to rewrite the code in a faster language. But a faster machine only makes each single check faster. It still checks every record. No fixed speedup can close a gap that keeps growing with n. Say we double the computer speed. The 17 minutes dropped to about 8.5 minutes. That is a small win. Now pick a better structure instead. The same job drops all the way to microseconds. That is a huge win. So when something is too slow, first ask what the operation is forced to touch. Then change how the data is organized so the work can be skipped. Do not just do the same work a little faster. This same idea runs the systems you use every day. Every layer of a real machine is really a data structure choice in disguise. An operating system must pick the next task by priority. For that it reaches for a heap, also called a priority queue, at big O of log n. A database must find one row by its key among millions. It uses what we call a B-tree index, again at big O of log n. A compiler must match every name to where it was declared. It uses a hash table, called a symbol table, at big O of 1. A network router must match an address to its longest prefix. It uses a trie at big O of L. A file system must walk folders and lists of free blocks. It uses trees and linked lists together. Each row here is really a chapter of this course. A data structure is a concrete way to organize data in memory, together with the operations that read and change it. There is one famous idea from Niklaus Wirth that sums up this whole field. An algorithm is only as good as the structure it runs on, and a structure is only useful for the operations it makes cheap. Wirth wrote it as a short formula. Programs equal algorithms plus data structures. The two always come as a pair. So one question comes back in every chapter. Which memory layout makes my operations cheaper? We always answer it in the same order. First the logical idea, then the layout in memory, then the cost. Think about cooking. The recipe is the algorithm, a list of steps. The organized kitchen is the data structure. Good steps still need organized data to run fast. Now that you see why this matters, here is the path we take. First, the logical view and the physical view, the idea of a structure versus the bytes in memory. Then abstract data types, where we describe a structure by what it does, not how it is built. Next, the cost model, which is how we measure work, using big O. And last, the C memory model, the stack, the heap and pointers. These four ideas are the foundation for every structure in the course.